Our topic today is energy in capacitors, how energy is stored in the electric field that capacitors have. Lifting an infinitesimal charge dq through a potential difference V requires the battery to do work, and thus increase the energy of the charge and capacitor system by some small amount du, which is just dq times V. And remember, that's our original definition of what V meant, which was how much energy per unit charge you had. All right. On the other hand, the voltage difference across the battery, or across the capacitor, depends on how much charge is already on the capacitor. The voltage at this moment is Q over C. Notice that we're adding a dq to an already existing charge Q. To find the energy to bring the capacitor to a total charge of large Q, we'd have to integrate. We'd have that dq, remember, is dq times V, which is dq times Q over C, because the voltage on a capacitor is its charge divided by the capacitance. So the total energy is, of course, just summing up all those little bits of energy as we add each little dq. So it's the integral from having no charge on the capacitor to having it fully charged of dq over C. C is, of course, a constant. That's the whole point. So it comes out front, and we're integrating q dq, which is 1/2 q squared. And when we evaluate from 0 to big Q, we end up with this very important relation, that the energy stored on the capacitor that has total charge Q and capacitance C is 1/2 Q squared over C. Why the factor of a half? One, that's the way integration works. Two, we can think of it this way. At first, the capacitor is nearly empty, and it takes almost no work to add another charge. But at the end, it's almost fully charged, and it takes a lot of work to add charge. In fact, right, because we're pushing against now Q. So on average, the charge is 1/2 the final charge, and so the average energy we'd have to add is 1/2 Q times Q. Of course, we know the charge, the capacitance, and the voltage are not independent, so there are multiple variations based on Q equals CV. This is sort of an annoying thing, and it's probably worthwhile to try and pick one of them to remember and then build the other ones as you need them. Although that's up to you. So we know that U is Q squared over 2C, but then Q over C is V, so it's 1/2 QV, and then it's 1/2 CV square, where this V now is the voltage across the fully charged capacitor. This last one, that U is a 1/2 CV square, is sort of interesting because it has the form of the energy stored in a spring, 1/2 kx squared. And in fact, we'll see later in circuits that capacitors often play the role of springs, storing energy and then releasing it in oscillatory fashion. By clever arrangement of circuit elements, it is possible to charge a capacitor slowly but discharge it quickly. We'll talk about charging and discharging capacitors later, but we really need to have the ability to talk about currents in circuits before we can do that. When we do this, we can use this, for instance, in a defibrillator. Those paddles you see on medical dramas when they slap the thing down and tell everyone, go clear. What they're doing is they're connecting those paddles to a very large capacitor, which charges relatively slowly, but discharges nearly instantaneously to relatively high stored energies of 100 or 200 or 300 joules. And you'll hear that if you watch various medical shows, you'll hear them say, charge to 300 joules. The idea is that it does take a while. It usually takes about a minute to fully charge, but it will discharge in milliseconds. And that's relatively easy to arrange, and we'll talk later in class about how. All right, a capacitor charged to 1.5 volts stores 2 millijoules of energy. If the capacitor is charged to 3 volts, it will store how much energy? And of course, we see here that we have doubled the voltage, and as a reminder, the energy is 1/2 the capacitance times the voltage squared. We've changed the voltage, but we've left the capacitance alone. All right, this is twice as much, but then squared, so we have 4 times as much. So we have E. A parallel plate capacitor with a given separation is attached to a battery until it's fully charged, and then detached. The separation is then doubled. What can be said of the energy stored in the capacitor? So our first thing is that by charging it to a given voltage, we have also charged it to a certain charge Q. When we detach the battery, it means there's no place for charge to come from or go to, so no matter what we do, the charge will have to stay constant, although the voltage can change. If we double the separation, we remember that the capacitance for parallel plate capacitors is epsilon naught A over D. By doubling the separation, we have made the capacitance become 1/2 as large. And then finally, we have the energy And we should use the one that we only change one thing. So remember, we have a half CV square, but we're changing C, and that will also change V. We have a half QV, but we're changing Q. We'd have to figure out V. I guess we're changing V. I guess we have to figure out what that does, and we don't have that directly. We have the capacitance changing, or we have Q is 1/2. U is 1/2 Q squared over C, and we can see that the Q squared now is not going to change. This is going to be half as large, so that U is going to become twice as large. Why does the energy go up? Well, one way to look at it is that we have we know it would take work to separate these things. We have to pull the two plates apart because one is positive and one is negative, so they'd rather go back together. And so we have to put work into the system to pull them apart, which means we're going to store energy in the system by so doing. That's a way to think about it. A different way to think about it is that by pulling them apart, we have we're not changing the charge density because we're not changing the number of charge or the area. And we're not changing the electric field between the two plates because that doesn't depend on anything but the charge density. So we have the electric field for twice as long as we had it before, twice the distance we had it before. Let's say this is our original capacitor, and then this is our new capacitor. The electric field is as strong, but now we have twice the distance, so we have twice the voltage. So we can also talk about that. Even though we've had the capacitor, we twice the voltage, which we square, and again we would get a total factor of 2. Parallel plate capacitor with a given separation is attached to a battery until it's fully charged. Separation is then doubled while the battery remains attached. What can be said of the energy stored in the capacitor now? Since it's attached to a battery, the voltage across the capacitor stays the same, even though we've made the capacitor larger. We said before, of course, the capacitor has become half as large. The capacitor has become 1/2 as large, same because it's the same situation. So we store half as much charge. Half our charge flows back into the battery. We can't maintain as much charge on it, even though we have the same voltage. Of course, since the voltage is staying constant, the logical thing would be to use the thing where that's constant, and so we can see that we have halved the capacitance, which is 1/2 the original energy. It has decreased. A way to think about that is that QV is less, since V is constant, but Q has gone down. And so we have less energy stored there. All right, an interesting and useful topic that leads into further studies that are mathematically fascinating is something called the energy density. The energy density of something is the potential energy divided by the volume in which it's stored. All right, that's the energy density. If we look here, the definition is energy stored or the volume which is stored. So for the parallel plate capacitor, remember we have plates of area A and separation D. The volume is A times D. And the energy stored is UC, of course. And so we end up getting that when we plug all these things in, we get 1/2 epsilon naught E squared. Remember, for the parallel plate capacitor, we have that the voltage is going to be the electric field times the distance. And, of course, the energy is 1/2 CV squared, which is 1/2 epsilon naught A over D times E d quantity squared, which is 1/2 epsilon naught A over D times E squared D squared, or 1/2 epsilon naught AD times E squared, which when we divide out by this, we get rid of everything else, and we just get 1/2. So UC over the volume is 1/2 epsilon naught E squared. That was scribbled pretty badly. I can probably do that a little better. Hold on. So we start with the idea that the voltage across the capacitor is its electric field times the separation. And then we go to the potential energy stored in the capacitor is 1/2 CV squared. CV squared, which is 1/2 times epsilon naught A over D times ED squared, which is 1/2 epsilon naught A times D times E squared. And then our potential energy density in the capacitor is that energy over the volume. So that energy over A times D, which is 1/2 epsilon naught A times D times E squared over A times D, or interestingly enough, 1/2 epsilon naught E squared. This means that we can consider energy to be stored in the electric field. And now the capacitor ends up being basically irrelevant by itself. We've derived this in a very hand-wavy way for a parallel plate capacitor, but in fact it's general at all. At any point in empty space where there is an electric field E, there's an energy density, which is 1/2 epsilon naught times that field strength squared. I put the note of empty because we'll come back later and see things are a little different if there is an insulator filling the space we're talking about, because the insulator can polarize. And we'll talk more about that later, so this will be modified, but will be modified in a very easy way. No matter what, the energy stored in the electric field is just proportional to the square of the electric field. That will be important, and its magnetic complement will be important too when we get to magnetism.